Sheshmani. We will talk about Atiyah class and sheaf counting on local Calabi Yau fourfolds.
Okay, thank you so much. I would like to thank the organizers for inviting me here. I should also thank the Laboratory of Neurosymmetry. I'm actually one of their international affiliates. I come here pretty often. I'm grateful for their support. So this is a joint work with Emmanuel Diaconescu, who is at Rutgers, and Professor Sheshmani. Okay. So this is about somehow enumerative geometry of Calabi Yau fourfolds and counting invariants, and it has to do actually with Higgs type moduli spaces or Mitchell type moduli spaces, which I actually studied later. So the basic ingredient and important ingredient of our counting theory on this Calabi Yau fourfold is Atiyah class, and I would like to just give you an overview, even though actually yesterday Vadim Valgotsky already told you guys everything I wanted to say. But since I organized my talk this way, I will repeat those things that Vadim already talked about. So let me tell you a little bit again about these Atiyah classes. Okay. Okay, so let's first discuss about the Atiyah class. This is the classical Atiyah class which was discussed yesterday by Vadim. And we start with some variety, x, projective, and a smooth variety. And we would like to consider the diagonal embedding of x inside x times x, and we associate this one ideal sheaf with the diagonal. We call it I of delta. And we can study the infinitesimal neighborhood of x inside this in this product. So we have O of 2 delta, which is basically O of x cross x mod I of delta. So this is the structure sheaf of first order neighborhood of diagonal in x cross x, and we know that it satisfies, it sits inside the short exact sequence, the canonical short exact sequence, which is actually the following. So O of 2 delta goes to O of delta, and the kernel of that is basically this conormal sheaf of diagonal inside x cross x. So this is the canonical short exact sequence that Vadim talked about yesterday. Now, we can look at, for any sheaf, this is the exact sequence that actually provides us Atiyah class of any coherent sheaf on x. So we can take a sheaf, F, a coherent sheaf on x, and then we can look at the two projections from here to here, and then we give this a name. So we can see that tensoring this exact sequence A with pullback of the sheaf to the diagonal keeps it as left exact. So preserves left exactness. Okay, so if we do that, so we can pull back the sheaf via this projection, and we will get the following. So we can tensor that exact sequence with this. So we get pullback of our sheaf, and then pullback of our sheaf times the structure sheaf of the diagonal. So this is remain left exact, and then we can project down everything onto X via the projection map P1. So if we do that, after projecting along P1, we will get, well, because F is supported on the diagonal, projection of the pullback will just give you F back. So here you will get F back. Here you will have P1 over lower star of pi P2 upper star of F times O of 2 delta. And here you will have F times first order sheaf of differentials of that diagonal. So this is what you get. And this is the short exact sequence that gives you the Atiyah class. So the set of possible short exact sequences like that are given by, so these are given by a vector space, a group, which is just extensions F1, F times F comma F times sheaf of differential maps. Which in fact you can also realize as a morphism in the draft category of X, because any extensions you have like that, you can also see that as a group it is homomorphic to, it's isomorphic to homomorphisms on the bounded draft category of X from given by F maps from F to F tensor, the sheaf of differentials shifted by. So these two things are actually the same. Okay. And Atiyah class, in fact, is a point of this vector space. It's an element of this group. So Atiyah class of F is in fact an element in this group. Okay. So what is it really? Again, this is something that Vadim talked about already. So I can put some words for it. So note that the map P2 inverse, I'm looking at that diagram over there, provides a homomorphism from local sections of this sheaf. Let's say U is some patch on X, some subset, open subset of X. So it gives you a map from local sections of your sheaf F to the sections on X times U intersecting with the diagonal of the pullback of your sheaf tensored with O of 2 delta. And by the projection formula, so by projection formula, you can actually rewrite the sections of pullback of F on this as sections of, this becomes isomorphic to sections of F over U, P1 over star of P2 upper star of F tensored with O of 2 delta. Okay, so as you can see, if I have an inverse map, P inverse, this actually kind of, looking at this short exact sequence, provides you a map from the right-hand side of that short exact sequence to the middle. So it provides you a splitting of that short exact sequence. Okay, so this provides a splitting of the short exact sequence. Okay, and then now, in which case, if, for instance, S is an OX linear splitting, then we can see that we can define some operator delta, which is nabla, which is S minus equal of inverse, and this induces via this splitting, induces a map from the quotient to the curve. So it induces a map from here to here. Okay, so this actually tells you, this actually you can now think of as a connection. So So lambda is a connection, is an algebraic connection on this sheaf F, and it's obvious by construction that Atiyah class of F then provides the obstruction to existence of such connection. So this is the classical Atiyah class, and in fact, it doesn't matter if you're replacing F with any complex of locally free sheaves. So if more generally, for any, let's call it F dot, an object in the bounded derived category of X, we can associate an Atiyah class. Which is given by we write it like this, and again it's an element of x1 on x f dot tensor of x. So this is the classical Atiyah class for objects in the derived category of x. Now, there is this notion of universal Atiyah class, which I will be using today, which is basically a lift of the classical Atiyah class of sheaves or complex of sheaves on a variety to the case where I replace sheaf of differentials of my variety with the cotangent complex of a variety. So in fact, if you replace omega of x with Iluzzi's cotangent complex, then you can define a notion of universal Atiyah class. Right. For instance, if your x is a singular variety, so let's do this. Let us now assume x is singular, in which case we would need cotangent complex of x. However, for my applications today, since I'm actually from these Atiyah classes and so on, I'm trying to compute invariance for my variety. I don't need the full Iluzzi's cotangent complex, but I need a truncation of the cotangent complex, and that's enough for my construction. And assume L dot of x tau bigger than 1 is the truncation of L dot of x in degrees bigger than equal to minus 1. So what that means, it means that if you have a singular variety, x, you can embed it inside some ambient smooth variety. So this is a smooth, and this is singular. And from this embedding, let's say you have the ideal sheaf of your embedding. This is ideal sheaf I delta or I of x inside A. And then your cotangent complex basically has a resolution which is given by this way. So you will have the sheaf of differentials of A restricted to x. This is a sheaf that sits in degree 0. And then you have conormal sheaf of this embedding of x inside A, which is I of delta, I of x squared. And this is in degree 0, minus 1. Of course, you will have many other terms. Probably you'll have infinitely many terms, but we are truncating this. We don't need it for our application. So basically, this is our definition of the truncated cotangent complex. Okay? And so now from this, similar to the notion of Atiyah class of a sheaf, I can define the universal Atiyah class. So similar to construction above, one can construct what is called universal truncated Atiyah class. Atiyah class of F for any f an object in the bounded graph category of our graph. This notion of universal truncated Atiyah class is due to Huybrechts and Richard Thomas. So Huybrechts and Thomas in 2010 defined this object, and we notationally we call it universal Atiyah class of f. And again, it is given by an extension over X between any object in the direct category F and F direct tensor product with the truncated potential complex. As a group on X, it's also isomorphic to a homomorphism in the direct category, which is, you can write it as a map from F to direct tensor product of F with truncated potential complex shifted by 1. Okay, so this is the universal Atiyah class of our sheaves.
Does not have any duplications of connections.
In terms of connections, not sure. I can construct it that way, but it's kind of it's involved. Spin and no, but it's not so obvious. Okay, so this is the object that I'm going to use, and you will see that it's very useful because somehow it actually gives you information about deformations and obstructions to deforming this object in the direct category on it. I will show you that at least. Okay, so now the notion I would like to use today is you also need the notion of universal truncated relative Atiyah class. Relative Atiyah class. Atiyah class, which we will be using today. So let me define that too. Let's say we have a product of two schemes. Like this. And let's say you would have some object in the derived category in here. So let's say you have some f in the bounded derived category of x times y. So one thing we can do, by the same construction, if you just replace x with the product of these two, you can define the notion of universal Atiyah class of f on this product scheme. So the universal Atiyah class of your f on x times y is basically simply given by x1 and f direct tensor product with L dot of x plus y shifted up. There's no shift, so this is just f. Okay? But then as x times y is a product between these two things, let me give these a name, P1 and P2, projections. Then you can see that the potential complex of x times y is basically pullback of potential complex. I mean, whenever I put, by the way, potential complex from now on, I really mean the truncation of it. So this is just given by direct sum of the pullbacks of the two potential complexes, like that. And then you can actually project this group onto the second factor in here. So via the projection of this direct sum to the second factor in here, you will get a projection to x1 f direct tensor product with the pullback of potential complex on y. And due to the fact that potential complex of y can be realized as the cone between the potential complex of the product of the two schemes and the pullback of potential complex of x, this object basically sees Atiyah class of x on here relative to x. So it basically sees only this part. So this is what we call universal truncated Atiyah class of f on x plus y relative to x. Is this clear? So basically, potential complex of y is the potential complex of x plus y relative to x. Okay. And why is this object useful? Because in our constructions, Y often plays the role of the certain moduli space, for instance, in our application, moduli space of sheaves on a variety X. And this F, which is the object in the bounded derived category, often will be just universal object on your moduli space. And so then you can, for a universal object in your moduli space, you can define some notion of relative universal truncated Atiyah class.
Why do you have a product in that situation? It doesn't seem to be useful to only define it for product.
I mean, for instance, for moduli spaces, it's actually product. On the product, on X times the moduli space, your F is basically some universal object parameterized.
Can you define more generally for relative, like without just that? Is it possible?
It is possible, but not for us in here. For us, it's just a product. So let me just replace Y with the moduli space. And you just see why is this universal relative Atiyah class useful after all. So let's, for instance, let Y be moduli space M of X. So this is going to be a moduli space, for instance, but this is an example. Moduli space of some sheaves on X with fixed numerical data, for instance, with fixed Chern factor, given by some vector omega. So if that's the case, then your universal Atiyah class relative to X will be just, this will be the universal sheaf on X plus N, and this will be the universal Atiyah class of the universal sheaf. Okay. So why is this object useful? I will now show you. It's a little trick by Verdier duality that actually sheds light on the application of this object. So maybe I make a remark. So remark. So if I start by this object, so I'm going to start from x1, x plus m, f, and then f tensor product with pullback of the truncated cotangent complex of my moduli space. I can write this as a homomorphism. So this is isomorphic to a homomorphism in the bounded derived category of X times the moduli space from F to F tensor pullback of the cotangent complex of my moduli space. And then it's just a fact in derived category that you can put this sheaf over here. So this is in fact isomorphic to, as a group, it's isomorphic to a homomorphism in the derived category of X times the moduli space. From this can move in here, and this will be a certain R between F and itself, and it isolates this pullback of this cotangent complex. So, okay. And now you can actually use Verdier duality. You're taking an R in some object, some self-extension of your universal sheaf on the product of X times M, and some pullback of this cotangent complex on X plus M, and then you can basically push forward everything down. Yes?
Artan, why did you shift?
Shift, yeah. Fantastic, thank you. Yes. And, well, now you can do Verdier duality and push everything via this projection P2 onto the moduli space and get the morphism between objects defined on the draft category of the moduli space. So by Verdier duality, by growth and Verdier duality, Verdier duality, this homomorphism is as a group isomorphic to on the bounded draft category of the moduli space only of R P2 lower star of R F tilde comma F tilde. Probably you need to tensor this with the relative dualizing complex here. So let's just say we do that. So this would be twisted by the relative dualizing complex, and then you will have only the cotangent complex of the moduli space shifted by one. And of course there is a shift by the relative degree of this projection via P2. The relative degree of this projection is just a dimension of the variety X. So let's say I shift this also by D, where D is defined as dimension over complex numbers of X. So okay, so then I can realize this morphism as R pi 2 lower star, R hom, F comma F, tensor with the relative dualizing complex shifted by D, and D minus 1 maybe, and then a morphism from that to the cotangent complex of my moduli. So let me give this morphism in the draft category a name. Field Y. Okay, so far I have produced out of the universal Atiyah class of the universal sheaf of the moduli space a morphism from this object to the cotangent complex of my moduli space. Let's call this one E dot of X. Okay, so why is this useful now? You can investigate the cohomological properties of this map from object E dot of X to L dot of X. After investigation, you can actually see that this morphism satisfies the following properties. In the H0 level, it is an isomorphism. And in H minus 1 level, it is going to be an epimorphism. That being for M, the moduli space of coherent sheaf of fixed Chern factor on the variety. And this is what is called in the literature as a deformation obstruction theory. It is an object in the draft category of the moduli space which fiber-wise over every point of the moduli space detects the deformations of those points parameterized by the moduli space. And the higher cohomologies detect the obstructions to those deformations. So this is the deformation, the so-called deformation obstruction theory. We have the notion of perfect deformation obstruction theory, and this so far doesn't need to be perfect. Not necessarily perfect. So as you can see, after all, the universal Atiyah class is a useful object because in this particular situation, it actually induces a deformation obstruction theory for your moduli space. There's also this work of Huygens and Thomas I mentioned, which actually says that the product of Atiyah class of a sheaf and the Kodaira-Spencer class of that sheaf always gives you obstruction class of deforming that sheaf. That I don't need in here because it's easier via the Verdier duality. The sequence of isomorphism automatically gives you this morphism of the draft category. So I don't need to necessarily talk about Kodaira-Spencer classes as such. Okay. So, very good. these deformation obstruction theories. So these have been studied extensively in the past. So deformation obstruction theories. So let me mention some of the developments. So if dimension D, if D is equal to 3, then Richard Thomas in fact showed that, in his thesis, showed that this object in the draft category does give us a deformation obstruction theory and also a perfect obstruction theory. What does perfect mean? It means that this object in the draft category can always be globally over-homogenized, must be quasi-isomorphic to a complex of given by two vector models. So it only has two non-vanishing cohomologies. So let me put that in here. So in case of threefolds, when determinant of our sheaves is fixed, Richard Thomas showed that phi of x from E dot of x to L dot of m provides a perfect deformation obstruction theory. Okay, so in the threefold case, this was done by Richard. Later, in the work of Hoibergs and Thomas, Hoibergs and Thomas showed that you can relax this condition. Hoibergs and Thomas showed that you can relax this fixed determinant condition, and in 2010 they showed that if you can show that if kernel of the canonical morphism from xi f comma f to hi of O of x, this is just a trace map. This is a trace map. Vanishes if the kernel of this morphism, this is the kernel, if this map vanishes, this vanishes for I bigger than or equal to 3, then again, phi of x provides a perfect deformation obstruction theory. Perfect deformation obstruction theory. Okay? Here you don't need necessarily Calabi Yau-ness or anything like that. You have the morphism, the trace morphism, which takes you from xi, f comma f to basically extensions of determinant of f comma determinant of f. Those are line bundles, so they cancel each other. So this is basically that. This is the ith cohomology of O. And the kernel of this thing is just a trace-free x. So this is what is called trace-free x of f comma f. If this trace-free part vanishes for I bigger than or equal to 3, then Hoibergs and Thomas, using their methodology, actually showed that using these universal Atiyah classes and so on, showed that you can apply a certain cohomological truncation to this thing and make sure that it's always isomorphic to, quasi-isomorphic to a complex of, to a two-term complex of vector models. So it provides them the means to basically construct a virtuous cycle and do integration and compute the invariance of the analysis. Okay, so this is that. My story today is about fourfolds, Calabi Yau fourfolds. So what happens when D is equal to 4? So first let me tell you the issue, and then I tell you what is it that we are doing today. if you look at the fibers of this object, this is basically just over every point of the moduli is giving you the self-extensions of your sheaf. So let me do a point-wise analysis. A point-wise analysis. If I look at that object and take cohomologies, basically you can see that you have, for your sheaves, you have homomorphisms, which capture the automorphisms of your sheaf. You have an x1 term, you have an x2 term, you have an x3 term, and you have x4 term. Okay? Let us assume that we are in a situation that our sheaves are stable. So homomorphisms are just given by C star, and somehow you can cohomologically truncate your potential, your object E dot of x and get rid of these. And I'm saying you can get rid of this thing because here I'm using Calabi Yau property. By Serre duality, you can actually see that these guys are isomorphic to each other, and this is self-cool. Okay, so if you can get rid of this one, assuming that it is just constant, that means that you can get rid of this one. Okay. Now you have an object in the derived category together with a map from this object to the cotangent complex, which naturally has three non-vanishing cohomology theorems. If it were the threefold case, you wouldn't see this thing in here, and you can see that this object has only two cohomology theories, so by suitable truncations you can always find the two-term complex of vector bundles that is quasi-isomorphic. But now you have three terms, and you don't know what to do. So the development in this particular direction was first done by Conan-Lung. So Conan-Lung and his student Yalom Sao. It actually suggested a very nifty kind of approach to deal with this kind of thing. They actually assumed that if you can show that this x2 part is written as a sum of some vector space, some isotropic half-real dimensional vector space. So let's say V is isotropic half-real dimensional subvector space, V inside x2. And if you can show that x2 is basically written as V plus V dual, then they showed that you can in fact cut this x2 in the middle and look at the complex whose cohomologies are this x1 and this yes.
What does half-real dimensional mean?
Half-real dimensional?
Yeah.
It just means half-real dimensional.
If you
Literally.
elaborate.
Yes, I mean, if you, for instance, if your vector space is two complex dimensional, V will be one complex dimensional.
Okay. So it's also half complex dimension.
No, half-real dimensional, I'm sorry. If your complex is one complex, if your x2 is one complex dimensional, V is just a half-real dimensional part.
Ah, so it's a real.
Yes, it's a real substance, it's a vector space.
Maybe it's half-dimensional.
Half-dimensional real substance. And then they showed that you can cut this thing in the middle, and you can construct some object in a derived category whose cohomologies are this x1 and this V. And together with a map. And so basically they were arguing that this you can think of as a local Coronicius structure, Coronician map. Similar to the Coronician maps between x1 and x2 in the old differential geometry literature. You can think of this locally as a Coronicius structure which induces locally a virtual cycle. And so this way they can construct locally over moduli space on virtual fundamental classes, and then they have to deal with the gluing of these cycles. And you cannot glue these cycles unless your moduli space is equipped with some higher homotopical structures. And this is where the language of derived algebraic geometry comes in. So this all fits inside derived algebraic geometry. Okay, and so Lung and Sao did this for the moduli space of vector bundles, and a big issue with the vector bundles is that if you start from a vector bundle, you can deform it, and almost never this vector bundle remains as a bundle. It becomes a reflexive sheaf, for instance. So you needed to be able to do these with sheaves, and that's why Joyce and his group in Oxford, actually one of whom is actually here, but right now he's not here. Joyce and Brav as well as Joyce and Dennis Borisov, who is actually my postdoc right now, they constructed this for moduli spaces of sheaves. In particular, for moduli spaces of sheaves and Calabi Yau fourfolds. Again, the flavor-wise, it is very similar, but it's structurally much more detailed than the work of Clement and stuff. Okay. So this is what you need to do, and you need to kind of use some fancy language of derived algebraic geometry to construct these virtual cycles over the moduli space. And this, I'm trying to say, this is something we do not want to do today. Okay? And in fact, one thing I should say, the virtual cycles that you construct using this technique lack so many properties of the virtual fundamental classes on the moduli spaces of, for instance, threefolds. For instance, localization theorem doesn't hold for them. The Graeber localization theorem does not hold for them. Degeneration techniques of Jun Lee, which he actually extended to the moduli space of sheaves, also doesn't work for them. These are things that are still remaining to be answered and to be constructed. It would be really nice if someone can actually do it. Okay, so the story today is that in some cases, you can avoid all of this fancy machinery and still use your regular algebraic geometry, even though you will be working on moduli spaces of sheaves on fourfolds. So, what is it we do today? Okay. So, for today, let us say that Y be a smooth quasi-projective variety. Projective variety. And let us assume that X is the total space of the canonical bundle of this variety over Y. And I give this projection a name Q. And let I be the embedding by the zero section of Y in X. Let us fix the dimension of complex dimension of X to be again equal to D. So I have a quasi-projective variety of dimension D minus 1 sitting inside a D-dimensional variety X. Okay. Now let us assume that M is the moduli space of sheaves, compactly supported sheaves on X. So what does that mean? It means that sheaves is stable, of the stable compactly supported sheaves. So that means that F have proper support in X, and we assume that, F is scheme theoretically supported on Y. Supported on Y. Okay, let's make an example. Let's say I have a divisor inside some ambient, a divisor Y inside some ambient variety X, such that the normal bundle of this divisor inside X is negative. And I'm looking at curves which are on Y. Now, as you can see, the negativity of this normal bundle doesn't allow the curves to have deformations outside of Y. So this is an example. Okay, but I will make another example. The particular example that I will be working with today, I will mention it in there. Let's say we have something like this. And so, how much time, by the way, do I have?
15 minutes.
15 minutes?
Yes.
Okay. So this condition, scheme theoretic support on Y implies that for any sheaf in this moduli space of coherent sheaves on X, let's say I fix some Chern character, then we can see that F is push forward of some compactly supported sheaf on Y. So where G is in coherent sheaves of Y. Again with fixed churn character that we fix, so such that churn of G is equal to that. Okay? Alright, so we have some situation like this. And so now we can see that we can view these modules on X as OX modules, torsion OX modules, or we can view them as properly compactly supported sheaves on Y, and they're both moduli spaces are literally the same. The two moduli spaces of these OY modules and the moduli space of these OX modules are literally the same, but we can put two different obstruction theories on these. So now we can have obstruction theories. So one of them is the one that we already studied. Phi of X is R pi over star. So let's say I have X times M, like this. And I have Y times M, which sits as a divisor inside this universal product, so inside this product. So these portions are the same, and these portions are the same. So let's call these two maps pi and pi prime, and this is a commutative diagram. So to this diagram, on the same moduli space, I can associate two different obstruction theories. So one of them is Phi of X, given as R pi over star of R hump, F tilde, shifted by omega of pi, shifted by d minus 1. This is the one that I constructed from universal Atiyah class of the universal sheaf. L dot of M. One of them is this one, and the other one is I can just do the same thing, because any sheaf I pick in here, it is literally given by the push forward of something coming from here. So in particular, universal sheaf itself can be pushed forward of universal sheaf on Y times M. So
is that sort of your definition of CP road support, or
which
or
definition?
what? I mean, so it's,
No, this is just implication. If your sheaves are spin theoretically supported on Y,
yeah.
then basically they all come from Y. So any sheaf can be realized as the push forward of something coming from Y. And that's how I call it G. I mean, there's basically effectively no difference between looking at these sheaves as OX modules or as OY modules. But the whole point is that these two moduli spaces, this is the moduli space of sheaves on Y with the fixed churn factor, and this is the moduli space of sheaves on X with the same churn factor. Really, these two moduli spaces are just isomorphic, because any OX module is literally a push forward by the zero section embedding of an OY module. But the object in drag category doesn't understand that. And so you can associate with this moduli space two different deformation obstruction theories.
In the derived category.
In the derived category,
Yeah. So it's not
the object doesn't understand this difference.
in general, the sheep is not necessarily a push forward.
No, it isn't. But here we are making an assumption that it is a push forward.
Okay.
Yeah. It isn't. Yes, of course it is. So R pi prime over star of R hump G tilde shifted by omega pi prime maybe. And this is d minus 2 because somehow y is one dimension less than x. So this will be d minus 2. And this will be L dot of n again. Okay, so you have two different deformation obstruction complexes associated with the same moduli space. Okay? Alright, so let me call this one, I called this one before E dot of x. And let me call this guy E dot of y. And let me at least show you the discrepancy between these two so that you can see why are these two things different. Okay? Again, I would like to show you this in a pointwise way. So comparison between E dot of x and E dot of y. One of them captures deformations of these sheets as OX modules, one of them captures deformations of them as OY modules. And how are they really different? Let's do a pointwise analysis. Okay, on the same moduli as M, I fix one of these sheets. So fix one of them. We know that by our assumption of a scheme theoretic support on Y, this is given as push forward of some sheet coming from Y. Now, some trick you can do is you can push forward G, but then you can pull it back to Y. So if you pull it back, you need to actually pull it back. You might get higher non-vanishing homologies. So you can pull back the push forward of G. And what do you see? You will see G itself, but then you will see something that detects the normal information of Y inside X. So you will get an exact triangle where this is G times co-normal bundle of Y inside X and shifted by Y. This exact triangle was proved to exist by Bondal and Orlov. And in fact, they showed that this exact triangle splits. This exact triangle splits in our case, where Y is given as a zero section of a bundle, zero section of a bundle. Okay? Now, the application of this exact sequence is that now you can apply R like comma G to it, to this exact triangle. Now what do you get? In the steps from here, you will get R GG, then you will get R pullback of the push forward of G comma G, this is the middle term, and then you will get R of that, R G. In fact, I can just move this to the right hand. So G times normal bundle of Y in X, and the shift by 1 will, because it's in the covariant coordinate, will be shift by -1. Okay, so this is what you will get. And now you can take cohomologies of this, and you can see that by the left adjointness of left drive pullback and the right drive push forward, this is the same thing as R you can move this here, I lower star of G, and by definition, this is just F, by our definition. So if you take cohomologies, you see that object that sits in the middle understands deformations and obstructions of these sheets F as OX modules. Object on the left-hand side sees the deformations and obstructions of those things as OY modules. And object on the right kind of basically sees the discrepancy of the two, which is caused by deformation of Y inside X. Now you might say that in our example, the example I didn't write, but I said maybe let's say Y has a negative normal bundle in X. These might not be actually contributing in the level of homomorphisms, which is true. If G's are stable, it will get vanishing if this normal bundle is negative. But it's not guaranteed. Maybe for higher cohomologies you see contributions. So as you can see, the object in the draft category does not understand really this fact that sheets are scheme theoretically supported on Y. So same moduli as this can have two different choices of obstruction units. Okay? Alright, so if I do this pointwise analysis in the families, I will get the following. So I will just put it, it's almost obvious, but I will not prove it. So all I need to do, I need to replace everything F and G with universal sheaf F and universal sheaf G. And I will get basically something like that. So in families, we will get something like R pi over star, R tilde shifted by d minus 1 becomes isomorphic to r pi prime over star r g tilde omega pi prime d minus 2 direct sum r pi prime over star r g tensor normal bundle y, and pull back d1 upper star normal bundle y shifted by, sorry, so this should be actually here. Oh, I will fix it. D minus 1 and d minus 1. Okay? So this is what I call E dot of x. This is what I call E dot of y. And let us call this thing the discrepancy complex, which is caused by a difference of y and x. So E dot of x is equal to E dot of y plus E dot of y x. Okay, so this is what we get. All right, so what does this mean in the level of invariance between invariance that we can define by these two obstruction theories? Of course, I haven't told you anything about the deformation obstruction theories. This is kind of very important. I have just compared for you E dot of x and E dot of y. But the deformation obstruction theory is more than just an object in a Graph category that captures deformations and obstructions. It's that object together with map to the potential complex. So in order to see the two deformation obstruction theories, you need to basically compare the maps that you get from here and the maps that you get from here. Okay? Are they equal, or are they basically the map? Are they somehow they can be decomposed as map from here to here and map from here to here? And that is actually our theorem. So I will put the theorem with no proof because it is kind of technical. Okay, so here's what we prove. Theorem. So we have Mescu and Yau. This is our paper appeared on our maybe yesterday or 2 days ago. And so here's what we prove. One thing I wanted to say is, in order to compare actually deformation obstruction theories, now I'm going to use the fact that via the Verdier duality isomorphisms I show you, it is enough to compare the universal Atiyah classes. After all, this morphism in the Graph category was induced by a universal Atiyah class of our sheaves, and same in here. So if I am able to compare the universal Atiyah classes, naturally, that automatically gives me also the map to the potential complex. So that provides me a comparison between obstruction theories. So the theorem I'm going to put in here is something about universal Atiyah classes right now. Okay, so consider universal Atiyah classes. One of them is universal Atiyah class of this universal sheaf, x times f m relative to x, and this is a point or an element of Artan in the Graph category of x plus m, f tensor with L dot I of the star of L dot of m shifted by 1, and the other one, universal Atiyah class of the universal sheaf G on y times m relative to y, and this is an element of Artan dE y times m G tensor with I prime upper star of L dot of m, again shifted by 1. Okay? So then we can see naturally that these two, similar to E dot of x, if you reverse engineer this identity via the Verdier duality isomorphisms, you can see that there's also a similar relation between those guys.
This is your theorem, so not.
Oh, this is what I'm writing. Yeah, so I will like to put it. So you have these two, and then there exists a composition. The composition of the following form. So Atiyah class of F on x cross m relative to x can be written as I tilde lower star of Atiyah class of G on y cross m relative to y plus the discrepancy term plus I lower star of some object R on dv of x cross m G tensor with I prime of the star of normal bundle of y and x, actually canonical y and x, G tensor L dot, shifted by one. Okay, so we can see that this identity holds true, and with respect to which this decomposition, Atiyah class. Okay, so maybe I should actually, this is kind of wrong statement, so maybe like I should say it like this. Atiyah class of F is an element, this is more correct, is an element of R F tilde L dot shifted by 1. And it has a decomposition, which itself has a decomposition as I lower star of R G tilde L dot shifted by 1. And Atiyah class of G actually sits inside here as an element. So the object in the graph can be satisfied with this identity, but Atiyah class is just a point in here. And with respect to this decomposition, we can see that Atiyah class of F becomes Atiyah class of G, comma 0. So in fact, this is what we prove, that if your sheets are string theoretically supported on Y, you can use this identity, but we are actually using it in the level of universal Atiyah classes. And as you compose this with the map to the cotangent complex provided by the Atiyah class, this morphism factors through this term, but doesn't see this term. So this doesn't exist. So you have a decomposition of vector spaces, one of which understands deformations of your sheets as OY modules, one of them understands deformations of your sheets as OX modules, plus discrepancy terms. But basically that decomposition tells you that a point in this vector space, which is realized by the Atiyah class, just maps to a point inside here, which is sitting inside this component and not the other. So only in the level of Atiyah classes, you can see a point goes to a point. If you make an assumption that your sheets are string theoretically supported on Y. And that basically has profound implications, because from that, you can see that same holds true for the deformation obstruction theories. So even though you have a decomposition of these objects, your obstruction theory doesn't see this discrepancy. And so a direct implication of this thing is that if you construct your virtual fundamental class of the moduli space via E dot of X, it actually matches to the virtual fundamental class of your moduli space if you use E dot of Y. Yes. So what does this imply? It implies that DT theory of X, which is a fourfold, so add some sheets on X with some fixed term character gamma, in fact match with DT theory of these sheets in Y, where Y is a threefold DT theory. So give me just 2 minutes to put one last consequence of this. So here is something that, as an application of this, we actually do. Which actually relates to Hitchin-type moduli spaces, Kaplan-Witten invariance, Vafa-Witten invariance, and all that, which is the following. So this is the example that we solved. So we start from some S, which is a smooth projective variety. Okay? And then we construct a threefold and we construct a fourfold on top of this S. So we have some X, let's say canonical bundle of S is Nef, and we pick some divisor inside S, which is effective. So effective divisor. And then we can construct some fourfold total in the space of K of S twisted by D plus OS minus D on S. This is our fourfold. And then we can construct a quasi-projective threefold inside this fourfold. So total in the space of only this piece. Okay, so this is our threefold. And then, as I said, my story is about compactly supported sheaves, proper support on X and Y, such that they don't have deformations outside of Y. So what are those things? Fixed sheaves, compactly supported sheaves, F in X, with Chern character given by 0, 0, 2 times class of S, some curve class, and some Euler characteristic.
So S is a surface.
S is a projective surface, complex surface.
Projective variety there.
Projective variety, a surface. Surface. Thank you. Okay? So I have a story about 4 manifolds. I have sheaves on this 4 manifold, codimension 2, in the realize that torsion codimension 2 sheaves on fourfold, and they hold the same Chern character inside Y. I can write their Chern character in Y as codimension 1 sheaves, so 0, 2 times class of the surface, beta n. And what we are proving is that invariance of these sheaves on the fourfold is the same as their invariance on the threefold. Okay. So we are showing that dt invariance of X is equal to dt invariance of Y. Now if S is K3, for instance, in our earlier works, the 2 papers we wrote with Professor Yau and Amit Goulampour, my collaborator at Maryland, we actually showed that via some localization techniques, these dty, these threefold invariants, these are Vafa-Witten invariants. So these are invariants, virtual count of the moduli space of solutions to Vafa-Witten equations on the projective surface. And you can actually see that some invariance of fourfold can be captured by Vafa-Witten invariance. Not only that, in our earlier work we showed that Vafa-Witten invariance relate to Seiberg-Witten invariance of the base surface plus certain correction terms, which are invariants of nested Hilbert schemes, for which we actually needed to construct virtual moduli theory for what is this nested Hilbert scheme, whatever it is. So the reason we are interested in fourfolds, this is my last sentence, is the following. If you do Vafa-Witten invariance on a surface, the solutions to the Vafa-Witten equations, for instance, for a Kähler surface, these can be written in the sense of Simpson equations. And the solutions, they have moduli space, and on the surface, for Vafa-Witten theory, you will get Hitchin-type pairs, which are like this. And via spectral construction, you can see actually that either you can count points of this moduli space, or you can basically do by a spectral construction, you will obtain sheaves on the total space of the canonical bundle of the circle, which is our threefold. And this threefold is threefold Y. So this is what we did in the earlier work. Now, if you did Kaplan-Witten equations, again you are looking at certain equations on the 4 manifold, but in that case your solutions are realized algebraically by hitching type pairs where this part is replaced by the cotangent bundle on the surface. So if you do a spectral construction, you will just get torsion sheaves, co-dimension 2 sheaves, supported set theoretically but not scheme theoretically on the base surface in an ambient non-compact fourfold. And you will be interested to count points, virtually count points of this moduli space, to be able to count vacuum the states of whatever quantum mechanics that you're doing on the surface. The point is that for fourfold theories, really, if you have either of the two ways. Either you need to use fancy language of derived algebraic geometry, or you need some intermediate step. And the intermediate step is that, okay, our sheaves are on the surface, they can deform outside of the surface, but can they deform outside of the threefold? Turns out not necessarily, sometimes. And if that is the case, then you can just collapse the fourfold to the threefold and compute invariance using the already available machinery of Donaldson-Thomas theory of threefold. And I stop it.
So is there a quick question?
Yeah.
I mean, I have this work with Graham and Fangaro, where we compare profit invariance of such a total space to exactly the ones in the box. So, we're saying that the complements of X you not invariance of Y with total tangency in the divisor D on Y.
Yeah, interesting.
Do you have any?
I can tell you some things about relations between Gromov-Witten invariance of X and Y. First of all, when you do Gromov-Witten theory on fourfolds, you know that higher than genus 1, you cannot, all your Gromov-Witten invariance.
Let's just do the 0.
So genus 0. Okay. So what I can say is the following. I think there is a notion, and we are actually working on that, there is a notion of MNOP correspondence between Donaldson-Thomas invariance and Gromov-Witten invariance for fourfolds. So if your fourfold has some intrinsic underlying surface, like say it's a rank 2 bundle on the surface, I can prove a certain Donaldson-Thomas Gromov-Witten correspondence for it, where basically I can show that Donaldson-Thomas invariance of X are equal to Gromov-Witten invariance of not the threefold, but S. So somehow Gromov-Witten theory of the surface captures fully Donaldson-Thomas theory of the fourfold. So the Gromov-Witten Donaldson-Thomas correspondence in the case of fourfolds suddenly becomes clear. It even relates to different dimensions. That's all I can say. But I like to hear about your Gromov-Witten invariance.
I mean, you say that they are exactly equal, so you don't have to choose.
No, the Donaldson-Thomas invariance, yes, but not Gromov-Witten. Gromov-Witten Donaldson-Thomas correspondence for fourfolds doesn't exist. For threefolds, it exists. For fourfolds, does not exist. If you want to prove some statement for fourfolds, we tried it, and we ended up with the surface. So somehow, for these fourfolds which are given as rank 2 bundles on the surface basically understands everything. That's what we are trying to say. Any invariant of fourfold, Donaldson-Thomas or not, for Gromov-Witten is understood by either Gromov-Witten invariance of surface, Savart-Witten invariance of the surface, or
the first
correction.
couldn't be straightforward. What I'm essentially telling you is we have a similar equality, however, on the right hand side we have to do y log d.
Okay. Log, no. Then I will. Yeah. Log, first of all, log dt theory. You know that. No. Okay.
That's very interesting. I mean, in program
Okay,
you have to
sorry,
choose the right hand
Edgar,
side.
maybe we should discuss privately later, just because we don't have much time. So I suggest we just stop here and we'll resume in 10 minutes. Okay?
Thank you for your attention.